In the previous lesson, we dealt with relative atomic masses, and then we used those masses to determine the molecular and formula masses of substances. We're still dealing with the knowledge area chemical change, and the information that we dealt with in the previous lesson is also going to be relevant for this lesson. We're going to look at chemical reactions. Right now, when we're looking at chemical reactions at an observable level, you find that certain things happen. Now, in order for what we see at an observable level, we need to be able to write an equation for it and represent that in symbolic terms. Let's look at balanced chemical equation. And we see a chemical equation actually represents a chemical change during a reaction. And there's conservation of atoms, right? That means the atoms we start with, we have to end up with as well. The total number that we start with, we need to end up with the same number. There's non-conservation of molecules. Molecules are not conserved in a chemical reaction. There's also non-conservation of volume. And the law of conservation of mass applies. Means mass, the total mass before the reaction is equal to the total mass after the reaction. And what we also need to do is balance the equations. Furthermore, we need to be able to interpret the equations. Now, a chemical equation does not give us any information about rate. Right, so if you have a balanced chemical equation, it doesn't tell you anything about how fast the reaction will go, how slow the reaction will go. That falls in the domain of kinetics. So from our balanced chemical reaction, you cannot infer what the rate of the reaction would be. Also, we do not know how or why reactions take place. The chemical equation doesn't tell us that. What does it tell us? It only tells us about the amounts of reactants, the states of the reactants in the product, whether the state is, whether it is in a solid state, a liquid state, or a gaseous state. Right, so before we go on to that, let's just look at a description at a macroscopic and a microscopic and a symbolic level. Macroscopic, microscopic, and a symbolic level. Let's look at this. Right, if you can see here, we've got water, we've got snow, and then we've got water vapor. Now, at a macroscopic level, you know you've got a liquid, you've got a solid, which is your snow, and then you have your water vapor in the air. So that's what you see, right? Now we need to interpret what we see. So in order to interpret what we see, we zoom into the microscopic world, and here we see if we're dealing with, for instance, a liquid here, we know we have a liquid, and see how the molecules are represented in a liquid. If we look at a solid, you can see there's a regular pattern in the solid. And if you look at gases, you'll see that the molecules are further apart, right? And these are all water molecules. So, getting back again to what you've done earlier in the year, you did the kinetic theory of matter, which gave you an indication of how these particles are arranged in the respective phases. And if we look at the symbolic level here, for instance, if we're looking at water in the liquid phase, we know then we write H2O liquid, right? So here we would have H2O liquid. There, because it's a solid, we say H2O solid, and there we have H2O gas. That's a symbolic form of what we see at a macroscopic level. Now let's look at chemical equations. A chemical equation, right? So we have a chemical reaction. It is a process of a chemical change, and it gives us an indication of the conversion of one substance to other substances. Right, so when we look at that and we symbolizing it here, that particular chemical reaction, we know we're moving from reactants to products. Now let's look at an example. If we look at an example here now, let's say we've got sodium. And sodium is a shiny metal. Right. If we take sodium and we drop it in water, we find that there is a vigorous reaction with water, and then what happens? Hydrogen gas is formed, and also we get sodium hydroxide left in solution. So at an observable level, here you've got sodium, here you have sodium, right? Just to show you this, I've got actually 3 alkali metals, but that's our sodium, right? So sodium is thrown into water, and as it's thrown into water, you find that it reacts vigorously with the water. And when it reacts vigorously with the water, hydrogen is given off. You can see bubbles at the bottom, and it gives off energy. And then the sodium hydroxide is actually in solution. So that's what happens at an observable level, at a macroscopic level. Now, how do we interpret this phenomenon in terms of what's happening at a microscopic level or the symbolic level? Right, so what we do here is, firstly, we know that sodium reacts with water, gives us sodium hydroxide and hydrogen. That we know, right? So what we do is we say, using chemical formulas provides a way to present quantitative information about the reaction concisely and unambiguously. So we've got this reaction happening at a macroscopic level, and qualitatively we know that sodium plus water gives us sodium hydroxide plus hydrogen. But quantitatively, we need to know exactly what happens, how much of each particular entity reacts. So at a symbolic level, we can summarize this chemical change. And we can say, okay, sodium, we know what its symbol, Na. And then we have water. And we know hydrogen is a product and sodium hydroxide is a product. So sodium plus water react, the arrow means reacts, and it gives us our product, sodium hydroxide and hydrogen. So this is really a skeletal equation. Right, now, to summarize this quantitatively, we need to note that atoms are neither created nor destroyed. Right? In a chemical reaction, they simply change their partner. Right, so if we look at that, we see we now, since atoms are neither created nor destroyed, in a classical sense, we see that we have here now 2Na. There's a coefficient in front here, and we have a coefficient there as well, and a coefficient there as well, which tells us we got 2Na atoms plus 2 H2O molecules, which react to give us 2 NaOH molecules or formula units, and it gives us hydrogen. Right, and in terms of this, you'll notice that the atoms are balanced, right? Since you have 2Na on the left hand side, you have 2Na on the right hand side, you got 4 hydrogens on the left, and you got 4 hydrogens on the right, and then you got 2 oxygens on the left and 2 oxygens on the right hand side. But if you look at it, you'll notice that you got on the left, you got 2 plus 2, 4 particles, and on the right, you got 2 plus 1, 3 particles. Right, now, the reaction also shows a physical state. So, that means if it's a solid, it's S. If it's a liquid, it's L. And if it's a gas, it's G. And if it's AQ, it means aqueous solution, meaning that the substance is in solution and the solvent is actually water. And most of our reactions in chemistry is going to take place in water. So you need to know what happens when molecular substances and ionic substances dissolve in water. So we see here that gives you a bit more information in the sense that it's saying we've got sodium solid, which reacts with water, the liquid, and it gives us NaOH aqueous, meaning that this is in solution, and that gives us plus it gives us hydrogen gas, which then leaves the solution. Right, so when we want to show that that a reaction requires high temperature, we can use the delta sign. Right, so sometimes that is what we do. We essentially see here we've got calcium carbonate in a solid phase, and then it decomposes to give us calcium oxide plus carbon dioxide. And what we normally do sometimes, we put the delta sign there, showing that heat needs to be supplied for this particular reaction to occur. And sometimes also we add a catalyst. And a catalyst is essentially a substance that increases the rate of a reaction, but a catalyst does not the catalyst increases the rate of the reaction, but it is not consumed in the reaction. So we normally, what we do is we just if it's a catalyst involved, we also put it on an arrow. Like for instance, if we have 2SO2 plus O2, which gives us sulfur trioxide, so sometimes we put a catalyst and we say V2O5 is normally a catalyst. Vanadium pentoxide is normally a catalyst that speeds up this particular reaction, but it's not consumed within that reaction, so we don't have to we merely just leave it and indicate that it's not part of that reaction. So a balanced chemical reaction equation symbolizes both the qualitative, right, and the quantitative changes that occur in a chemical reaction. The stoichiometric coefficients, right, that's the numbers in front, tells us the relative numbers of moles of reactants and products taking part in the reaction. So these are our stoichiometric coefficients. Oxygen here, there's we don't have to write 1, so the coefficient of O2 is 1, and then the coefficient of SO3 is 2. Now let's go to the law of conservation of mass. So the law says that the total mass before a reaction is equal to the total mass after a reaction. Okay, so let's illustrate that. Here again, that would be at a microscopic level where we showing these particles of peroxide. We've got 2 of the peroxide particles, and when it decomposes, it gives us 2 water molecules and 1 oxygen molecule. Right, which means if we have, for instance, we say 2, right, and we know what the relative atomic masses of hydrogen is, so it's 2 times 1, plus we know oxygen, it's 2, and we know what its relative atomic mass is. Relative atomic mass, and that gives us 2, which gives us 2 right, plus 2 times that. So if we look at this, here we got 2 plus 32 is 34, and times 2 gives us 68. And here we have 2, right? So it's 16 times 2 is 32, right? So that gives us 34. I'm sorry about that. Which gives us, right? It gives us right. So that gives us 2 times 18 plus 32, which is then 36 plus 32, which then gives us 68. So the total mass before is equal to the total mass after the reaction. Let's go to the next one. Here we have the water molecule, and in terms of this, again, we can illustrate the same thing where we've got 2, so 1 plus 16, and that gives us 2 times 2 times 1 plus 2 times 16, which would then be 18 times 2, which is 36. And here we got 4 plus 32, which also gives us 36. So we can see there that we have the mass of our reactants is equal to the mass of our products. Now let's look at, but just coming back here again, you'll see in this situation our atoms are balanced, but our molecules are not. We got 2 molecules here, there's 2 molecules, and there's 1 molecule. So there are 3 molecules there, and there are 2 molecules here. So while the molecules are not balanced, but the number of atoms of the respective types are balanced. We've got 4 hydrogens on the left, we've got 4 hydrogens on the right, we've got 2 oxygens on the left, and we've got 2 oxygens on the right. Now let's go to a volume relationship of gases in a reaction. So if reactants and or products are gases, we can get a volume relationship. Now the volume of a mole of gas at STP is equal to 22,4 decimeter cubed. So we know that 1 decimeter cubed is equal to 1 liter. So for a mole of gas, right, at STP, it occupies 22.4 decimeter cubed. At standard temperature and pressure, and what standard temperature? It's 0 degrees Celsius and 101.3 kilopascals. That's under those conditions, 1 mole of a gas will have 22.4 decimeter cubed volume. Right, but what is a mole? So a mole is essentially a counting number, right? The mole is essentially a counting number, and it is the SI unit for the amount of substance. And a mole contains 6.023, let's just do that. It contains, thus here, it's an exact number. Now you'll see your textbook still define the mole in terms of carbon 12, the carbon 12 isotope. From the 20th of May 2019, the mole has been redefined. It's no more in terms of the carbon 12 atom. What has happened when this committee met? The 7 basic SI units have been redefined in terms of natural constants. So first, our mole was defined in terms of carbon 12. Now it's no more linked to carbon 12, it's directly linked to this constant here, which is known as Avogadro's constant, and we will be dealing with it. So if I say give me a mole of particles, what I'm asking for is 6.0221476. That's exact, but we are normally only going to use it to 2 decimal places. So 6.02, right? 6.02 for our purposes. So 1 mole of any substance is equal to 6.02 times 10 to the 23 particles of that substance. So if I ask you for 1 mole of apples, it would be 6.02 times 10 to the 23 apples. If I ask you for 1 mole of marbles, it would be 6.02 times 10 to the 23 marbles. So the mole is essentially a counting number, but you'll in our future lessons I'll show you that the mole is actually determined by mass. So mass actually is a proxy for this particular number. Right, now let's look at nitrogen. So nitrogen we have here reacting with ammonia, right? So as you can see, I've got 2 nitrogens, and I've also got 2 nitrogens here. Again, I'm showing you this at just a microscopic description of it. And the hydrogens I've got is 1, 2, 3, 4, 5, 6. I've also got 1, 2, 3, 4, 5, 6. So you can see the atoms are balanced, right? So it means essentially I've got 1 of those plus 3 of that, and it gives me 2 of that, right? So 1 plus that gives me 2 of that. But if you look at the molecules here, you'll see on my left hand side I've got 4 molecules, and on my right hand side I've got 2 molecules. So molecules are not conserved in a reaction, but the atoms are. Now, if this is, which is, I mean, we know nitrogen is a gas, hydrogen is a gas, ammonia is a gas. When this reacts, let's have a look at this. We'll see we got 1 and 2. We don't have to write 1 plus 3 H2 gives us 2 NH3, which essentially, what am I saying here? Symbolically, 1 particle of N2 plus 3 particles of H2 gives me 2 particles of NH3. So I could say for short, 1 particle of that plus 3 particles of that gives me 2 particles of this. That would be the ratio or the relative amounts of each. Or I could say maybe if I want to have more, I could say 1,000 particles of that with 3,000 particles of that will give me 2,000 particles of ammonia. It's one way of saying it. Another way we could say is 6.02 times 10 to the 23 particles of nitrogen plus 3 times 6.02 times 10 to the 23, 10 to the 20, 10 to the 20, 10 to the 23 particles of H2 will give me 2 times 6.02 times 10 to the 23 let's just do that again. Will give me 2 times 6.02 times 10 to the 23 particles of ammonia. But we know that 1 mole of a substance occupies 22,4 decimeter cubed. So if we want to have a volume relationship, I could say, for instance, let's say I know 6.02 times 10 to the 23 particles would imply 1 mole, and that occupies 22.4 decimeter cubed. So if I could say it's 1 volume of nitrogen plus 3 volumes of hydrogen gives me 2 volumes of ammonia. That's a volume relationship. And as you can see, as I have indicated earlier, the volumes are not conserved. Right, so 1 plus 3, we then end up with a product that has a lower volume. So it could be that I start with 1 liter of nitrogen plus 3 liters of hydrogen. I end up at the end with 2 liters of ammonia. Alright, here we have O2, right, water being electrolyzed. So at a macroscopic level, you've got water being electrolyzed, and we see that we've got hydrogen gas there and oxygen gas here, right? And energy is being supplied, the water is being electrolyzed, and you got hydrogen and oxygen. You'll also notice that in terms of the gas that's in here, the volume, and the gas that's in here, the hydrogen, the volume of the hydrogen gas is twice that of the oxygen. Which means, for instance, if we have to now interpret this reaction, we say H2O liquid, and what has happened, we supplied energy to it. So we supply energy, so we can even say plus energy. In this case, it's electrical energy, and that gives us H2 gas plus O2 gas, right? And if we look at the equation and see if it's balanced, we find that it is not balanced. So what have we got? We got 2 hydrogens on the left, we got 2 hydrogens on the right, right? So if you want to balance it, we have to have 2 hydrogens there, which gives us 4 hydrogens, and which gives us on the right only 2, which means now we got 4 hydrogens on the left, and if we look on the right, we have 2 oxygens on the right, and we have 2 oxygens on the left. So there we have that particular reaction given symbolically, right? Now let's go to the exercise. If you look at the exercise, let's check out the law of conservation of mass using relative atomic masses. So we have 2, so we got 14 for nitrogen, right? Plus hydrogen, we know is 1, which then gives us nitrogen two times 14 for nitrogen plus 3 that, and which gives us that. So we got 2 and 17, which gives us 34, and here we got 28 plus 6, and that also gives us 34. So the law of conservation applies. And if we look at it again, we see the molecules are not conserved, and we see that the volume is not conserved, right? The state of these molecules have not been given here. Let's look at the next one. We got MgO, which then reacts to give us Mg and O2. So we have two. Now magnesium, let's go quickly to the top there. Magnesium, right? You've got magnesium, and you'll see here's magnesium. Its relative atomic mass is 24. You know that oxygen's is 16. Okay? All right. So okay, let's go there to, so we have, so it's 24 plus 16 gives us 2 times 24 plus 2 times 16. So here we have 2 times 40 gives us 48 plus 32. So that gives us 80, and that gives us 80. Alright. So again here we find that that law applies. Right, now let's look at this one here. We got calcium chloride plus sodium carbonate gives us calcium carbonate plus NaCl. Alright, so calcium is 40 plus chlorine, we know is 2 times 30 5.5, okay, plus 2 times 23 plus 12 plus 3 times 16, which means here we have 40 plus 71, right, plus 46 plus 12 plus 48. So if I look at this here, right, that is for this, which means here we have 117, and for this one we have 106. So it's 48, 50, 60, 106, which means in total we got sorry here, I just see what I've done. So it's 111 and 106, which gives us 217 for the reactants. Alright, 217 for the reactants. Let's look at for the products. So for the products we got CaCO3, right? So that would mean if I say CO, right, here we have 40 plus 12 plus 3 times 16. Okay, that's the first part. And then plus we have 2 into 23 plus 35.5, which then gives us here it's 40 plus 12 plus 48, and 48, that gives us in total 100. Alright, and here we got plus 2 into 58, it's 58.5, alright, 58.5, and that gives us 1, right, 0, 1, 0, no, 1, 1, 1, 1, 1, 7, which then gives us 217. So the mass before it's reacting is 217, and the mass after it reacts is 217. Alright, now let's look at hydrogen peroxide. If we look at hydrogen peroxide here, hydrogen peroxide is taking place right at the macro level. You can see it decomposes, and when it decomposes, it gives off oxygen and it gives off hydrogen. So we know we have here in this situation, we have H2O2, which is a liquid, right? And then it gives us H2O, the liquid, as well, plus it gives us O2, oxygen gas. Right, that's how we would show it at a symbolic level, right? So you have H2O2, and if you look at this, we need to balance it. So that would be 2H2O, and that would be 2. So we got 4 hydrogens on the left, we got 4 hydrogens on the right, we got 2 oxygens, 4 oxygens, and we got 4 oxygens. So there's balance, right? And we have done this, so we don't need to go into getting the masses on both sides. Then we go to iron sulfate, sulfide, sorry, not sulfate, sulfide. So here you got iron, right? And there you got your sulfur, which is a yellowish powder, and it reacts, and when you heat it, you get FeS. Right, so at the macro level, you know how these substances look, and when they react, it gives us iron sulfide, right? So you can have a macroscopic description of that particular reaction. But let's see how we would write this down at a symbolic level. Right, which would mean, for instance, we would say now, we could say Fe, which is a solid, plus sulfur, which is a solid, gives us FeS, which is a solid. So that's balanced. If you look at that, that's balanced. And if we look at iron and see what its mass is, right, going all the way there. Right, if we look at iron here, its mass is 56, right? And if we look at sulfur, the mass is 32. Okay, so that's 56 plus 32, which is then gives us 88, right? And it's equal to 88 there. Right, so that gives us that, but sometimes iron, whilst I've written it here as sulfur, like a sulfur atom in a sense, sulfur normally is a molecular solid and it exists as S8, which means it's actually Fe solid plus S8 solid gives me FeS, Fe gives me FeS. Right, so the ratio in which it combines is still the same. So you have S8 there, S, so we have put the 8 in front, which will give me 8, and I have a 8 here as well, which means 8 Fe plus S8 gives me 8 FeS, right? Which is the same thing like saying 8 times 56 plus 8 times 32 will give me 8 times 80, 8 times 88, 8 times 88, 8 times 88. So if you really look at that, and which means if I cancel that out, cancel that out, cancel that out, then the ratio is the same. Okay? Right, now let's look at the exercise and let's balance the following reactions. Here we got NO2, NO, which is a gas, and it's a gas, right? Oxygen is a gas, NO2 is a gas, right? The state of these substances haven't been given. So if we look at this, there's NO plus O2, and that gives us NO2, right? So we got 2 oxygens on the right, we got 2 oxygens on the left, 3 oxygens on the left, so we need to balance the oxygens. So by inspection, we say, all right, I've got 2 there, and I've got 2 there, which then means 2 nitrogens on the left, 2 on the right, and then 4 oxygens on the right, and 4 oxygens on the left. Let's look at the next one. Right, here again the state isn't given. Right, since we're only going to be concentrating on the balancing, here we got diphosphorus pentoxide plus water, which gives us phosphoric acid. And if we look at that, we then see we've got 3 hydrogens on the right, 2 on the left, but we got 2 oxygens, 2 phosphorus on the left and 1 on the right. So to balance that will give us 3 there and 2 here. And it will give us 2 there. Right, this here is potassium chlorate, and that normally is a solid, right? And potassium chloride is also a solid, and oxygen is a gas. We balance that reaction, we see we got 3 oxygens on the left and 2 on the right, and if we balance that, let's use a different color, so it gives me 2 of that and 2 KCl, which means I've got 2 Ks, 2 Ks, 2 Cl, but I've got 6 oxygens on the left and I've only got 2, so it's 3O2, and that's balanced. Let's look at the next one. Here's manganese plus Hi, hydrogen iodide. which gives us hydrogen plus manganese iodide. And if we balance that, we see that we got 3 iodines on the right, but only 1 on the left. So in order to balance that, we have 2 Mn, and then 6H, which then gives us 3H2, and it gives us 2MnI3. So you got 2Mn, got 6 iodines on the left, and I've got 6 iodines on the right. And I've got 6 hydrogens on the right and 6 hydrogens on the left. Let's look at the next one. Here we got hydrogen cyanide plus copper sulfate gives me sulfuric acid plus copper cyanide. Now, sometimes how I like to balance this, if I see a group like that, so I know there's 2 of that, and so I normally like to take it as a group, and that would give me 2H on the left, 2H on the right. I've got a sulfate here, 1 sulfate there, and that's balanced. Let's look at the next one. Here we then have rubidium nitrate and beryllium fluoride, giving us beryllium nitrate and rubidium fluoride. If we look at again here, I like to look at it as 2 nitrates, so I put a 2 there, right? And that would then, if I put a 2 there, so I will need to put a 2 in front of the rubidium. So I've got 2 fluorines, and 1 beryllium and 1 beryllium, right? This one we've revisited several times. That gives us 2 and 2 H2O. Let's go to the next one. If we look at Na plus Cl2, that gives us NaCl. This is a fairly easy one. We've got 2 chlorines on the left and 1 on the right. So we balance that. We got 2 and 2. So 2 Na on the left, 2 Na on the right, 2 chlorines on the right, and 2 chlorines on the left. Now let's look at this reaction here. This reaction is a combustion reaction. You got C3H8, that's actually propane gas, which reacts with oxygen and gives us carbon dioxide plus water plus a lot of energy. So this reaction is actually exothermic, and that energy that's given off can then do mechanical work or heat a system, whatever the work is required for. So here we have that gas, that's a gas, that's a gas, and that's a liquid. If you look at this, we got 3 carbons on the left, we got only 1 on the right, and we want to balance that, we can put a 3 there. Once we balance the carbons, we got 8 hydrogens on the left and 2 on the right. We can then put the coefficient in front, which gives us 8 hydrogens. And if we look at the oxygens, then we've got 6 plus 4 oxygens on the right, which is 10, and then we need to balance that, which gives us 5O2. Let's look at the next one. It's again a combustion reaction again, but you probably recognize it, C6H12O6, right? That's glucose, and when it reacts with oxygen, gives us H2O plus CO2 plus energy, right? It also generates energy, and it's an exothermic reaction as well. So here we have again, okay, but in this case, that's a solid, that would be a gas, that's a liquid, and that would be a gas. if we balance this, we see that we have then right, we got 6, so we got 6 carbon dioxide, and we got 6 carbons on the left, 6 carbons on the right, and we got 12 hydrogens on the left, so we need to put a 6 there, which gives us 12 hydrogens on the right. And if we look at our oxygens on the right, we got 12 plus 6 is 18, and here we've got 6, so we can put a coefficient in front of oxygen, which then gives us 6, which is 12 plus 6 is 18, and that is balanced. Let's look at the next one. Here all your states have been given. Potassium sulfide is in aqueous solution, right? Meaning that dissolves in water. Zinc chloride is also in solution. Potassium chloride is also in solution, but zinc sulfide is a solid. It doesn't dissolve in water, so we have indicated it as a solid there. If we look at the balancing, we've got 2K potassiums on the left and only 1 on the right, so we balance that, and now we got 2. So if we look at the remainder, we see 2K, 2K, 1S, 1S, 1 zinc, and that is balanced. Let's look at a different one. Here it says a reaction between reactant A, right? Reactant A, blue spheres. So A is actually blue spheres. So that's going to be A squared. And reactant B is red. Reactant B is red. If we have to write an equation for this, we're going to say A that, but we got how many of it? 4, right? And we got 4 of B, and that gives us 4, right? 4 of A squared B, right? And then that reduces to A that plus B, which then gives us A B, right? Which would be that one. Okay, that brings us to the end of the session, and see you next time.